discussed various aspects of compactifications of the theory of gravity, and what kind of brains do we get. Now it's time to apply all this to the most interesting case, namely, we would like to compare (11-dimensional) supergravity compactified on S1 of radius r small with 10-dimensional superstring field. On R. And we would like to compare fields and brains. And what I will tell you is that here you will see some interesting coincidences. We will be able to identify parameters of these two theories, and it will give us two equations relating parameters. And after identification, we will find three mysterious coincidences. So it would be already a computation confirming this duality. And this duality is in the core of what is called U-duality. In M theory. So that's where we are going. So the plan of my talk would be the following. First, I'll give you some facts about 11-dimensional supergravity. Second, facts about superstring. And then we will start comparison. And I hope you'll be surprised to see that this comparison works. At the moment, there is no conceptual explanation of this phenomenon. It is just empirical observation. So empirical observation would be that not only fields coincide, but also tensions of brains coincide. Okay? So let me start with 11-dimensional supergravity. It has the following fields. GMM, 11-dimensional mix. C, M, and T. So that is A3, 4. And that's all if we consider bosonic fields. And also gravitino, that is fermionic, and I'm not going to talk about it right now. Moreover, I'm not going to talk about gravity. because it's an introductory lecture. You need to get feeling for what's going on. Now, how people got it? People were trying to study supersymmetric theories and studied representation of the supersymmetric algebra on massless particles, and they found that it goes like this. I'm not going to talk about it. So please trust me here. Now, since we have a three form, we have a two-brane charge with respect to C. Now we assume that there is also a five-brane magnetically charged with respect to C. It's easy to compute why this should be a five-brane. So in duality, generalized F equals F dual equals star of F, and if we have P form for C, that is a P form, F, that is dc, is P plus 1 form, and in dimension D, F dual is D minus P plus 1 form, okay? So it means that C dual is, of course, D minus P plus 1 minus 1. Now, let us take 3. Now, P equals 3, D equals 11. So here we have 11 minus 5 is 6. And due to this, these bad notations of English scientists, we call this six-dimensional object the five-brane. Okay? Now, such theory has only one coupling constant, that is M11, or M plus 11, and I still have place here. The action of 11-dimensional theory is M11 to degree 9 integral r square root of g plus dc star dc, actually plus some other terms, but I'll omit them. There is so-called Chern-Simons term in C, but I will omit it because it's the first time when you probably see it. Now why we put m11 to the power 9? Because R has dimension 2. And altogether we need to have dimension 11. So I will use this dimension counting in my talk. So any questions? Actually, that's all that you need to know about 11-dimensional supergravity. No, not all. You see, I say that there is a two brane charge. I will put it here. Tension of this two brane should be m11 cube. Once again, two brane is twice has, so would it be a particle? Its mass would be m11. Would it be a string? Its tension would be m11 squared. So it's a two brane. Its tension is m11 cube. And similarly, tension of the 5 brane equals m11 6. I'm thinking where to put the rest of material. I'll put it here. So this is a preview, I think. So let us see what happens if we consider 11-dimensional supergraph compactified on S1 of radius R. So now we have the second parameter, R. It's a radius. Of 11th dimension. What will be field? What will be the fields that you will get? We will get G11, 11. That will be a scale. Okay? G11, U. That will be a one form. We will get C11 mu. Now this will be a 2 form. And we will have C mu lambda. And this will be a 3. Okay?
Also, G mu.
And also, of course, we will have also G. So here we have something that we understand as forms, and here we have metric. Of course we have metric. Now, what about grades? First, we consider G. You want to do something?
I want to take the chalk. I think there's.
Ah, sure. So you
Yeah,
get,
no?
I have enough shot. So we already studied that there are particles charged with respect to G11. Now, these particles are Kaluza-Klein modes. And the tension of these Kaluza-Klein modes is 1 over R. Now we have C11 mu. And it's a two-fold. So how to get charged brane? We just take a two brane and wrap it around the circle. Two brane that is wrapped. And of course, the tension of this brane is R times M11 U. Okay? So it has dimension of mass square, as it should have. And this is, of course, a one brane, also called string. Now what else do we have? We have C mu lambda, and of course we have two brane unwrapped with the tension M11 Q. Okay. So these were electrically charged. And now, what about magnetically charged? So let us go in order. Unfortunately, I erased this computation. So let me consider 5 brane wrapped. So it is a 4 brane. So sorry, 2 brane unwrapped. So there is a 5 brane wrapped, and this is a 4 brane. And this is magnetically charged with respect to what? I say that it is magnetically charged with respect to C mu lambda. Let me make a computation again, showing that magnetically charged brane for this is a fourth brane in dimension 10, of course, because we are making compactification. So C is a 3 form, DC is a 4 form.
Wait, shouldn't it be a six brane magnetic that is coupled to this
So the C mu lambda, it's a 3 form, and it is a 2 brane coupled. Because of this crazy English notation.
Yeah, but this, when we consider it under electromagnetic duality, we said that the 5 brane is like magnetically charged with respect to the 3 form. That means a 6 brane should be charged with respect to a 2 form. not
6 brane, where do you see, at the moment I have only 5 brane.
Where did you get 4 brane?
4 brane, I'm getting 4 brane in the phone, I'm reading.
Ah,
5 brane
okay.
direct.
Okay.
So once again, C is a 3 form, DC is a 4 form. Star DC is a 6 form. So that's why C dual is a 5 form. And what is charged with respect to the 5 form is, sorry English people, it's a 4 brane. This is because of crazy English notation. So it is magnetically charged with respect to C. Now, we have another object. That is 5 brane. By the way, when we say 4 brane magnetically charged with respect to C, we should immediately write down its tension. M11.6, since it's wrapped, times R, right? You see. So here I have 5 brane. And interestingly, that this 5 brane is magnetically charged with respect to C mu 11. And its tension is, it has a tension M11.6. And interestingly enough, we also have 6 brane. Six brane is, I write it here, tau naught, or gross pairing. Tau naught gross pairing monopole why it is, I need to explain why it is a sixth grade. I'll draw a picture. We have my favorite picture, like this. This happens in 4 dimensions. Now, 11 minus 4 is 7. Times R7. So 4-dimensional picture is like this. And once again, English rule. This thing spreads these 7 dimensions. So that's why it is a sixth grade. Okay? And of course, it is magnetically charged with respect to, that is magnetically charged with respect to G11U. It is a monopole.
So, what's this figure means?
What this picture means?
Yeah.
It is tau black magic. Tau black configuration. It is the following configuration. Its base is R3, its fiber is circle almost everywhere. But at some point, this circle shrinks. So this thing, fiber over R3, is by way to draw a Gross-Perry or tau knot. So for tau knot it was an instanton because it has a finite action. For Gross-Perry it was a monopole. So Gross-Perry considered it in 5 dimensional sphere. And they had only arcs. So for them it was a part. But now it is a sixth grade. And it is easy to compute its tension. You see, we are not showing the brain that is charged. We also compute its tension. So how to compute its tension? Let us take the action for 11-dimensional supergravity. Okay? And here is the radius r. So everything is proportional to this r. Okay? So curvature. Curvature is 1 over r to the second power, right? Now the area where you have this curvature, so this is r square root of g integrated goes like 1 over r squared. It's a curvature, and you multiply by r to the 4th. It's the area one. So you are getting r squared. So just plugging this metric into the action, we are getting contribution M11 to the 9 times R squared, and this is the tension of the 6th grade. So that's why I put here M11 to the 9 times R squared. Okay? So, in this way, I describe the spectrum of fields and branes that are charged with respect to these fields. I am trying to be as elementary as possible. Tim, any questions? So the question is why Englishmen invented this shifted notation, which I cannot answer. So here we have numbers. 1, 2, 3, 4, 5, 6. And these 6 numbers look kind chaotic, okay? Sometimes we have R, sometimes we have whatever R, sometimes we have R, sometimes we have R squared, okay? But I explained how I derived them from 11-dimensional spectrum. And then we get the last data. And this last data is for the scattering of gravitons in 10 dimensions. Yes, 10 would be, of course, M11 to the 9 times R. So this would be the Planck mass to the power 8 in 10-dimensional compactified gravity. How I am getting this small r? I am just integrating. So actually I have not only 6, I have 7 now. And then my goal would be to reproduce these 7 numbers from the string theory interpretation of the same phenomenon. Okay? So we should make breaks at some point. So we started.
Only 35 minutes.
Okay, good.
I have a few questions.
Yes,
First of all,
please.
So what about this scalar? What does it mean? Is it
So it is definitely a scalar.
Okay, so
So the expectation value of this scalar is the radius of the 11th dimension.
hmm,
So how you measure the 11th dimension? You take this G1111 and you integrate.
it's probably something like R squared.
Yes, yes.
One more question. So suppose we were to compose, so the circle is kind of flat, there's no curvature.
Yes.
But suppose we were to complexify a sphere of radius r. We would have to take that curvature into account. That's 1 over r squared curvature,
So,
right?
so we have only one good compactification here. This compactification. Because this compactification also preserves supersymmetry. And if we would compactify on a sphere, it's not very easy to preserve supersymmetry. In general, you would not preserve supersymmetry. But people say, okay, we can compactify on different things. We can compactify on circle, on torus. So it's easy, and we will discuss it. And we can also compactify on K3 manifold. And if we compactify on K3 manifolds, K3 manifolds live in the real dimension form. They preserve supersymmetry, and we will get something interesting. But at the moment, I'm doing the simplest thing. I'm compactifying on a circle. And in the introduction to M theory, I will be compactifying on a circle or on a product of circles. It is enough to show a lot of rich phenomena.
Can I ask? So you choose this tension of two brane and five brane theory as M11 to 306, but don't they have the extra free parameters? So dimension-wise, this is right, but M2 brane can be M11 to 3 times some dimensions parameter.
Dimensions.
Yeah.
Okay, we don't know. So at the moment, I am doing everything up to dimensionless parameters that would be like world number. So would there be, say, I don't know, 17 as a number? We will say that 17 is the world number in M theory.
So it not necessarily an integer. And we are talking about extra free parameter.
So here we can in principle get dimensionless parameter. But postulate here is that this dimensionless parameter is like 1.
Nice.
Okay. Maybe it will be convenient for me to make a break right now. Okay? Not 45 minutes plus 45 minutes. Okay, but say 40 plus 50. Because here you have 11-dimensional supergravity compactified on a circle. And then we will study string. In the same fashion, very elemental. You do not need to be a rocket scientist to understand. So I will call this spectrum data. Like in particle physics, you have charges and masses. Okay, here we have differential forms instead of charges, and tensions instead of masses. And that's how things look like.
I have a question.
Yes?
So why was that gravitational field for running?
It is fermionic by definition. In supersymmetric theory, supersymmetry is an odd symmetry. It takes bosons into Fermi. So supergravity is a theory where you have bosonic fields and fermionic fields, and supersymmetry takes one into another.
And shouldn't there also be used as a partner to this three form C?
Gravitinum,
It's O. It's supposed to
Yes.
be partner to G and to C.
yes, it's superpartner to G and to C together.
Mm-hmm.
So when people say that it's a superpartner only to metric, it's not quite right. It is like this only in dimension 4 in the minimal supergravity. But here we live in dimension 11. So people called it gravitinum in dimension 4. Now let us come.
Just to be clear, this G11.1 gets coupled to zero branes, which are particles,
Yes?
just like in the Kaluza time.
Yes? It's
Just to,
written.
yeah, I understand. Just to, the racking, 1 over R. Okay. And also, yeah, in the original, before compactification, we said that there was some free form and some two brane charged
Yes.
with respect to
It's the
the
next
form.
one.
Okay, yeah. And, Alright.
Okay. So now let me tell you some basic facts about string theory. People say in string theory that particles correspond to these closed circles, and these closed circles scatter in such a way, and this amplitude is proportional to G string of 2, okay, to the power of minus Euler number to minus Euler number of the surface. Yes. So Euler number of the surface, and here there is an important clue. Yes. So Euler number of sphere is of course 2. Euler number of a torus is 0. Euler number of genus G given surface is 2 minus Tg.
But before we count this other characteristic, we should add like caps on the,
No, we should not.
no?
However, there is a possibility to have, okay, so now it depends. So they correspond, okay, right. We need to cut these caps, taking one point out. But I think it's the same as not cutting, not collapsing the caps.
Well, the sphere has another characteristic too, but the cylinder has another characteristic 0.
Yes.
So we just have one closed string propagating cylinder would have a different characteristic than cylinder.
Yes. So I think you are right. So in this case, yes, you are right. We need to close the caps. We need to close the caps. Yes, here I was wrong. We need to close the caps. But this is kind of a vacuum trap. Now let us see what happens if we have a scattering probe. I just want to say that Euler number of this is what? I want it to be 2, I think. So what is the Euler number of the vertex? Minus 1. Okay, in this case, let me consider this. Let me consider this diagram. We have Euler number -1 here, Euler number -1 here. So such diagram would have Euler number so I think I would not like to close caps. So here I would like to have Euler number of such thing, let me call this sigma, to be equal to its -2. So here I have G string to the power 2.
The upper graph has a genus inside.
Okay, so you see, I put here I put here the loop, I can also draw the same diagram with the loop. So let us study some examples. So how loop is going on? In terms of particles, the loop is something like this. Now we replace, so now we see only these vertices. So number of these vertices is 1, 2, 3, 4. 4 vertices. So for each vertex, I am getting G. 3. Yes, G string. So for this diagram, I will get G string to the power 4. And here, with this picture, I am coming in agreement with the concept of scattering amplitude and gravity. And what I put here mass of the string to the power 8. And here I write G, or G square root of G. Sorry, suppose the action is like this. And if I have such an action, I will have exactly the same count. Of G is dependent. Why do I have it? Because I can decompose, okay? I go from bottom to top.
What's the dimension of GS? Is it dimension?
Of course it's dimensionless. Because it's unreasonable to put dimension for something to the... Okay, so now I'll try to explain something on a very general ground. Suppose I have an action that is some nonlinear function of field phi, and here I have 1 over G, I'll call it G naught squared. Then I will decompose it as follows. Quadratic polynomial on phi plus cubic polynomial on phi plus etc. And then I will make a rescaling. I will go from, I will call field phi over G naught. I will call it field phi tilde. So then this object will go into S2 of phi tilde plus G naught S3 of phi tilde plus G naught squared S4 of phi tilde, etc. Right? So that's why for cubic vertices I will have G naught, for quartic vertices I'll have G naught squared, etc. And I would like to compare it with what I have in strings. And I see that they represent the same computation. So to get the same computation, I just need to say that G naught goes to the minus Euler characteristic of sigma. Because of these pictures. So the action for the string perspective is like this. Let me call it string perspective. I put 1 over G string square here. I assume that I will get gravity, and I'll put here ms to the power 8 to have something dimensionless. So in this way, I already have some number that may be compared with the number on the left hand side. Maybe I need to draw it in red letters. 1 here and 1 here. Comparing red ones, I see that m11 to the 9th r should be equal to ms to the 8th gs. Okay? So on the string side, I have two parameters, ms and gs. On the 11-dimensional side, I have two parameters, m11 and r. I need to have, so I'd like to make 7 comparisons. If I'll make 7 comparisons between systems that has 2 parameters, I have predictive power. But it was only about gravity. Now, I need to say something about field in string theory. Point A, bosonic. The action of the bosonic string is written in terms of the metric plus rho times phi. What is this? This is the metric in the space. What is this? This is a 2-form. And this BMN of X field is called Kalb-Ramond field, and it corresponds to the field that charges bosonic string. Now, what is this field phi? So I need to say what rho is. A rho is to D curvature. Now expectation value of phi, if we change expectation value of phi, we change our famous number. That is GS to the Euler character. So that's why we expect that this field phi of x, at least its constant mode, is related to this scalar. Okay? So let me underline it by orange. I have this, and this. Let me find them in the space of forms. So, I already found the scalar. I already found C11 mu, that is a two form. And I have a metric. So orange is bosonic string. Now, let me go B to superstring. I need to say something about superstring. At a very elementary level. If you have a string, you have so-called vertex operator. And this vertex operator describes the coupling of the string to external fields. We already have seen here three vertex operators, namely orange. Vertex operators in superstring are very simple, are constructed like this. A. You have so-called left moving sector. You have right moving sector. And you have special vertex operator. I'm simplifying a little bit, but special vertex operator is phi of x. Now, what about left moving sector? In the left moving sector, we have vertex operator that is Vm in bosonic string. But in superstring, we also have S alpha. Oh, sorry. Superstring should be underlined by blue. It is a spinner. And this is the one. Now vertex operators in superstring. Comes from Solr, we call it V left. V superstring are just V left, tensor V right. So that is Vm, okay, I'll call it V plus S, left, tensor, V plus S right. Now what we have? We have V left. From this we have V left, tensor V right. And V left tensor V right is exactly the orange piece. Because vector times vector is vector times vector symmetric plus vector times vector antisymmetric. Vector times vector symmetric is metric. Vector times vector antisymmetric is this BMI field. Of course, say V left times S right would give gravitino the time not gravity, the time not studied here. Interesting thing happens when we have S left times S right. So what does that mean? It means that we have two spinors. If we have two spinors, we need to decompose the product of two spinors to understand what does it mean. And people who know something about gamma matrices knows that product of two spinors would be decomposed as a sum of representations of the algebra to some external powers. Okay? How does it happen? You take spinor, and you put here gamma matrices. Gamma M1, gamma MK. And here we take a scalar product. And of course, this depending on if you take here, you say L and R was from left and right moving sectors in this structure. Depending on if both are left or right spinors in terms of representations of SOG, in our case in SO10, we can have either even number of gamma matrices or odd number of gamma matrices. It is an idea. So in the string theory that we will discuss, number of gamma matrices is odd. So it means that we have fields called Ramond field. Or simply RR field. That are one form, three form, five form, here I would like to go to seven form, but yes, seven form, and there is also some subtleties about nine form. Here I put this question mark for some reason. It's not easy to understand it, and I will not study it today, but I'll have this one form, three form, five form, and seven form. Now let me underline it by blue. Okay, so here I will underline it like this.
So sorry. They independent. What I mean, so you insert many gamma matrices, and if we insert one gamma matrix, it's one form. And if we insert
Yes.
but if we insert seven gamma matrices, and if you assume chirality is definite chirality, it's same as insert
Yes.
three. So 3 form and 7 form are same.
Yes.
I see.
So you may speak about relations, but for me it is important to tell you that there are these forms that appear here, and we actually see these forms. Okay. Now, what can I say about what is charged and what is not charged? I already see that bosonic string is charged under the bosonic string itself. This one. So orange is the bosonic string, is charged under the 2,4. It is from the very beginning. Now, let me say something about what objects are charged with respect to other forms. So where should I write it? I'll write it here. I am not going to derive it, but here I ask you to believe me, because I'll consider it as an axiom. In string theory, it is possible to study, how to call it, to study branes charged under Ramond form. in superstring theory. Derivation of this fact is not simple, that's why I'll omit it. And these branes have a stringy origin. These branes are so-called D branes. And they correspond to the following rule. String could end on them. While they are kind of mysterious, we can immediately get their attention. Suppose we have two D branes. How would they interact? I just draw a cylinder connecting. So, cylinder has Euler number is 0. So interaction between D branes goes like G string to the power of 0. But if I try to write it down in from the gravitational perspective, I would draw it like this. So here, here I will draw at each coefficient tension of a D brane squared times G string squared. Because for any object in gravitational theory, here I use brown. The gravitational interaction goes like this. Here I have GS for emitting graviton, and here I have GS for receiving graviton. And the vertex is attention. So that's how two masses are attracted in Einstein theory. So that's why I conclude the rule TD is ms to some power divided by gs. You see in this picture, I keep MS fixed, and I'm trying to understand this rule of interaction between two D branes. Okay, I remember this one. Now, basically, it's all I need to start making my theoretical experiment. How I understand zero brane. I understand zero brane as D brane. So its tension should be MS over G. And I call this formula 2. But where do I have here? I have it here. This is my formula 2.
Sorry, can you say again why tension to D brane is MS to the sum power? Why is it over GS? The first power GS.
It's because the division by GS should compensate GS that is involved in the emission of the gradient.
But doesn't GS account for this only characteristic of some Riemann surface? How
Yes,
does-
so altogether, since the Riemann surface that connects two D branes has Euler characteristic 0, then GS should go away. However, when we try to consider it as a heavy object, we should write tension of it squared times GS squared. So that's why tension is 1 over GS.
Why do we square the tension?
Why do we square the tension? Because of this diagram. Here is the gravity. Here we have tension 1. Here we have tension 2. Here we put GS for emitting the gravity. And here we put GS for absorbing the gravity. That's why this process should go as T1, T2, GS squared. At the same time, it should go as GS to the power 0. That's why T goes like 1 over GS. But you see, now I'm making prediction that's 2 equals to 2. So I have this relation. I can go further, and I see the 2 grain red should be a string. So I have 1 grain. So that is a string. So it has tension ms squared. This is formula 3. Moreover, I have 2 grains. That is D grain. So it has ms cubed over gs. And this is the formula 4. So already, without going to higher brains, I have 4 relations. Let me check if it would work out. So first of all, how can I check?
How do you get the ms squared for the string?
Because the tension of a string is a ms squared.
And it's not a D brain.
Of course, it's not a D brain, it's a string.
Ah. Okay.
Let me say take 3 and 4 together. Okay? From 3 and 4 together, so I forgot to write 3 and 4. From 3 and 4 together, I see, what do I see?
No, I think in this one is to multiply 2 by 3. So 2 by 3 should equal to 4 if you multiply 2 and 3.
Okay,
So that kind of thing was consistency relation.
2 by 3 is 4.
Yes. So that's true for pink ones
And 2 by 3,
is 4. So you kind of checked one consistency relation. So you can exclude 4 for the price of 2 and 3. So it is consistent on both sides.
okay, but so I just want to say that here I have consistency.
Yep.
And it's important that I have consistency, or another way to see consistency.
Yeah, you can multiply 2, let's see.
So,
Say 3 and 4 square, so then you should get 1.
so the easiest, so I have very easy relations. By the way, okay, so I can multiply it in this way. However, I had relation 1 that I had not checked yet. So what is the
You
relation?
can multiply 3 and 4 squared to get 1.
I can multiply 3 and 4 squared.
To get 1.
And I'm getting 1. Yes.
And that's true on both sides.
Yes. So already here I produced 2 consistency checks. But I can go along with this prediction because what about 3 break? From the point of view of string theory, it should be ms to the 4th over gs. And this is the formula 5. Okay? Ah, I'm sorry, there is no 3 braid in the business. No 3 braid. There is only 4 braid. Only 4 braid. So 4 braid has ms to the 5th power over gs. This is 4. Because D brains is this one and this one. Now here we have 5. Do we reproduce 5?
Yeah, you can multiply 4 and 5 to get 1.
I can multiply
4 and 5
4 and 5
to get 1.
to get 1, yes. Okay. Now what about 5 braid? We have an interesting thing. We have a 5 braid here with tension M11 to the 6th. What does it mean on the string side? It's definitely not a D braid. And the tension is, in string theory units, I square equation 4, it is ms to the 6th divided by gs squared. So it is not a D braid, it is something else. It is called an S braid. So you see, braid that is magnetically dual to string in string theory picture is not a D braid. So string itself is not a D braid. And it has tension just ms squared without dividing by gs. And an S braid is not a D braid. So what we know is it is not a D braid. And perturbative string theory is not giving us any clue on what it is. But we can still continue. Now there is a sixth brain. Okay, so here it's not a test, it's just an observation. Okay? And here we have another test. We have this tau naught instanton, that is m11 to the 9th r squared. Could it be a sixth brain? So would it be a sixth brain and should have a tension M7 to GS? So what is the simplest way to see that it is like this?
So multiply 6 by 2.
6 by 2.
2 should be 1.
No, I want here. I need to multiply it here to get to reproduce it. So I need to get M string MS7 divided by GS. And I want to get,
So you need to divide 1 by 2.
so where is my 1?
So 1 is on that block in supergravity.
Yes. So if I divide 1 by 2, yes, it is 1 by 2. So in string theory perspective, 1 was what? I had it. I erased it.
No, it's here on top left port, top upper left on upper
Yes.
port.
So I divide 1, no, but it is on the string side.
So string side on the right board, on right upper board.
So on the string side, so this is a string side, and I need to divide on the string side 1 by 2. Yes. So on the string side, I divide 1 by 2. On the gravity side, yes, on the gravity side, I also divide 1 by 2. Yes. So it works. Now, I have an extra confirmation that I'm talking about D-brain. And this should be the end of today's class. Let me come back to my favorite picture of tau naught. Okay? What if you will have two tau naughts together, close to each other? Now I would like to have Venice would look like this. Actually, this metric is known as Eguchi-Hansen metric. So 2 tau knots at a finite distance. So it is a hyperkähler metric on T star to CP1. Then what can you have? You can have a two-brane that wraps the sphere. So from the gravity point of view, we have a two-brane that wraps two spheres. From the superstring theory, so D branes are blue, and another is blue, and yellow is a string. So wrapped, two brane becomes a string. Places when fiber collapses become places where string could collapse. And we have a nice picture explaining that it's really working like this for 6 branes. So, where we understand gravitational origin of the D brane, we can see that it is a D brane. Well, where we do not have this, so what can we say? So this is the end of the exercise that I want to do with you. So there are many checks of this U-duality conjecture. That it works. Together with the prediction of mysterious 5 brane. With a tension 1 over G squared. That's it. That's all, folks. So now questions. You may go through these computations by your own. And it is highly recommended. So if you go to the literature, you will see some fractional powers in this comparison. I do not need it. So in the literature, people try to work in 10-dimensional Planck masses. And you see, if you put your 10-dimensional Planck mass, you will have a mass in computation. But here, everything is as clear as it could even be.
So those blue points are the 0 branes.
No, there are not 0 planes. Remember,
But
I
they're
have
deep.
this multiplied by R7. So there are 7-dimensional manifolds. So this is 11-dimensional space. We take out 4 coordinates and 7 coordinates. Nothing happens in this 7 coordinates. In this 4 coordinates, we have exactly this job. So the result here is 2 parallel D branes, 2 parallel D6 branes.
And this is just a parallel, it's not,
Here, they are parallel in our set.
no, I mean, is it a parallel to this, or is it exactly those 6 branes that,
These are exactly those things. Because we discussed that 6 branes from gravitational point of view are tau knot configurations. And from the string theory point of view, such pair of tau knots correspond to a D brane. So string could end here and here. So string is understood as a wrapped 2 brane. But if 2 branes wrapped around something, it could end somewhere. So from the string theory perspective, we see it like string that starts somewhere and ends somewhere. So here we can actually see this. See that this is actually a D brane. Not only because of their tension, but also because it is a D brane. However, it's very non-trivial to try to understand why 0 branes are weak. To see that this is non-trivial, please note that tau knot stuff was classical stuff that we understand. And the 0 brane were Kaluza-Klein models. This is not classical stuff. We have Planck constant somewhere. Let me here also mention one thing that would be used later on. That string stretched between two parallel B-brane is like a particle. One of its spatial dimension is fixed. And this particle has a mass. So this mass is either the tension of the string stretched between two D-branes, or just the area of this sphere. I could make another remark here. This picture is good for strings that are far away, for how to say it, for tips of taubna that are far away. So we have intermediate region, and then we go along like a cylinder. However, when I take two things together, this solution doesn't have enough time to develop the full cylinder. And it goes like this. Maybe here it goes to the cylinder. So the region where I do have a picture of the cylinder is of course where R is small. So R, when R is small, in comparison with this distance. So it means that I have D-brane picture for small r's. But I just want to note that there is equation 2. That G is proportional to R. So string coupling constant is proportional to the radius of the 11th circle. So we can believe in string theory consideration only if this radius is small. However, the conjecture says that we need to believe in it everywhere. But that's why configuration like this where distance between D-brane is much smaller than R, may be thought of as something non-perturbative. Because you need to measure this R with respect to something. And there are many other questions that you may ask. So my goal was just to give you an introduction into this business. And that's why, despite of these facts, working with M theory is kind of an art. So this art started 30 years ago, and still it is an art. But you need to know it. So that's it. So in the morning we discussed U-dwells. It's called type 2A superstring. And here I had M11R. And here I had G that I'll call A. So that is R, and here I'll put M strings divided by M11. No, M11 divided. I think I made some mistake here. G8. Falsify mode. And strings. And also M string square was R and M11 cubed. Okay. Now we will study the following thing. We will study T-dual. And then we will study identity, 11-dimensional subgraph that would be compactified on the terms SR1 times SR2. So the first thing that we will study, and this is the second thing that we will study. And we will find here S-dual. because this would be equal to times 2b superstring superstring with g b equal to R1 over R2. And here I will put on S1. S1 RB. And it will be interesting to see what RB is. So I will correct myself, but something like this. Okay. So now let me explain it. In the simplest possible way. Suppose we have a theory on a circle of radius r. And suppose we have a string then in such theory I will definitely have 1 over r that are Kaluza line particles and I will also have r times m string squared widening mode. So this form tau and this form tau. And T-duality says that it is possible to interchange these models. So string theory compactified on S1 of radius R is isomorphic to string theory compactified on so string theory has M string with the same M string so I need to have radius. and I will add something. Here there will be superstring theory of type A, and here would be superstring theory of type B. So superstring theory of type A were superstring theory that we studied. Then what are superstring theory of type B? Type B means that they have the following fields: G mu, B mu, phi. So these were orange. And also C mu, okay, phi tilde, C mu, and C mu u lambda rho.
Wait, so orange were the same one as in type A?
Orange are the same as in bosonic.
Mhm.
Now these guys also come from SL times SR. However, now chirality of SL and SR are the same. Now, in type 2B string theory, it's interesting to see that we have doubles, phi and phi tilde, C mu and B mu. Well, this is singlet and this is singlet. So we will see, is it reasonable to group things together? So in type B theory, there are you may call D minus 1 brains, but we will not study them. There is also D1 brain. And there is also D3 brain. So T-duality could be proven not only by this hand-waving argument, but more rigorously. But I just don't want to do it today. I will prove it next time. Okay? Meanwhile, what I just like to mention. I just like to mention that this is T-duality, and in this T-duality we have extra rule that I will not prove today, I will prove it next time. You see, D brains have different dimensionality. That wrapped brain goes to placed brain. So what does this mean? It means It means that if in the theory type A, I have a brain that is placed on a circle, it goes to the brain wrap. And if I study with the brain wrapped, it goes to the brain plate. And next time we will derive this rule. But now I just want to take this rule as granted. Okay?
Can we have at least some intuition with, say, a brain that is wrapped twice? Would it go to a different point, or to 2 points, or to...
Brain that is wrapped twice would go to a double point. So double point or wrapped or brain wrapped twice is called the stack of the brains. You see, in order to derive this rule, I need to speak about two-dimensional conformal field theory, and I just don't want to do it right now. Okay? So let me assume that we understand it.
And what happened with the tension when it's wrapped? We thought that it's kind of multiplication by R. The tension is old one.
I mean the brain wrap, not the fundamental structure. Okay.
But deep brains also have tension.
Yes.
So what, is there some kind of rule?
So, and we know the tensions of deep brains.
Yeah, but when it's wrapped, it's kind of multiplied in the simplest dimensional basis. It's like multiplication by R.
You see, when I go from this to this, I have two different radius. So here I have RA, and here I have RB, so that is 1 over RA m string squared. So it is not geometrical duality. Let us see how it goes. Kaluza-Klein modes go to winding modes. So something non-geometrical is going with the space-time. Now, let me study the following thing. Let me study M theory, 11-dimensional Subra compactified on SR1 times SR2. And I can do it in two ways. First, I study this compactification, and then this compactification, or all the way around. Okay? So if I start with doing first R1, I will get, I will say 2A with GS that is, so I had it. R times MS.
R1.
What?
R1.
Yes. And of course, this MS so I need to recall some formulas. MS square was R1 times M11U. So I may write out of it MS is R1 1/2, M11 3/2, plug it here, and then I will get GS being R1 3/2 M11 3/2. Yes. Okay. So what would happen if I compactify it on this one with the radius R2? I will have 2A theory with this GS and some R2. Now with the mass equals R1 1/2 and 11 0. Then I will do T dual in R2. So what will I get? I'll get the theory of the type 2B So actually GS would change, but I am not telling you how it would change. GS, we will see. Would go to GS tilde. MS is still R1, 1/2, M11, 3/2, and then R2. What happens with R2? It is 1. Okay. R2 would be new R2. Would be, let me call it R2B. Would be 1 over the first R1, and here I put MS squared. R1 by cube. I am applying this formula.
One of those should be Q, because it's type A modular as RQ1.
1 second.
You should be,
So tension was like this.
Yeah, it's right.
Now I put tension squared in denominator.
Yeah, it's right. No.
So this is tension squared in denominator. Ah,
it should be,
it should be R2 here.
actually, the formulas you gave before, it was 1 over the product of radii times the cube of it.
For what?
For 1 over, for RV. Yeah, see? 1 over RV, you wrote this M1, M11 cubed times R1.
But if you just, this formula, this
Yeah,
formula,
yeah, now,
No math.
okay.
now, let me do the following. Let me study and this is a compactification from 11-dimensional Sugra on S1 R1 times S1 R2 to type B over S and now this is very interesting. So what is interesting about this formula? First interesting thing is that here R1, R2 symmetry is restored. Okay? Now, what kind of, so it is to be, and of course with tension. Ms is, however, tension tension is not invariant under change of R1 and R2. Now let us see what kind of branes do we have here. In 11-dimensional subra, we have the following branes. First, like above, we have Kaluza line. And this Kaluza line, particles of this type and of this type. Okay? I'm sorry. I said it wrong. I said it wrong. I'm wrong. So when I study Kaluza-Klein in simplification, so Kaluza-Klein masses correspond to eigenvalues of Laplacian. In this case, 1/8. Now, or probably I got it right. So what are eigenvalues?
Why not always?
Because we understand the 11-dimensional subgraph.
That's, okay.
So after we made two dualities, we would like to inspect what is going on.
So just as before, we had eigenvalues of Laplacian on a circle, now we have two circles, right?
Yes. So probably I said it right. So eigenvalues would be, so but I need to say Kaluza-Klein from the point of view. I need to erase something. I would like to have two boards. The left board would be for superstrings. The right board would be for 11-dimensional supergravity. So in 11-dimensional supergravity, we of course have Kaluza-Klein particles. And I'm sorry, I was right. Of type 1/R1, 1/R2, and there could be something like p squared over R1 squared plus q squared over R2 squared. Second type of particles that you will have here. Two brane wrapped over the torus. And two brane wrapped over the torus would give Kaluza-Klein particles, would give particles of the following type: M11 Q, R1, R2. 3. With still a particle. But then we will have strings, one branes. So how can we get these one branes? We can wrap two brane over XR1 and place in XR2. But we can also do the same thing over XR2 and place in XR1. So tension of first brane would be M11Q R1. Tension of the second brane would be M11Q R2. Okay?
Because you have a lot more one cycle control, so you can have
Yes,
each
yes,
cycle.
yes. And the sum says I can have something like this. So typically I will have PQ strings with tension M1, M11Q, and here I will have R1 square plus times P square.
No.
No, it is without square, just the length. You want
No.
total length. Okay.
So here is the picture when this length is R1, here I have twice R2, and I have a string that wraps. Okay? And let me see what would I have on the superstring side. I will have dilute supply particles. 1/RB. And we already have this RB. That is R1, R2, M11. Okay. We have interesting information. Now, what about brains? I have this brain and this brain. So it's a tension. Tension 1 and tension 2. On the superstring side, I decided to rewrite. I have string with tension ms squared equal to R1 M11 cube. And what about the second string? What this could be? I am going to the blue chalk. Yes. What this could be? I'll have D1 gray with tension R2 M11 cube. So I understand it as ms squared times R2 over R1. Right? And since it's a D brain, I would say that I have only one way to understand what is going on, because it is ms squared divided by G string B, where G string B is R1 over R2. And I will write it in purple. So making this analysis, I see that the string point of view on this compactification says that string coupling constant is the ratio of two radii. And now I say, wow, it is something great. Because on the side of 11-dimensional subgraph, I have a geometric symmetry. R1 and R2 interchange. So it means that theory with GB is equivalent to the theory with GB minus 1. And this is called S-duality. So it is clear that when I do this, I can see how it goes. And I may see that this S-duality interchanges B and C field here, clearly. And this is the place where S-duality just comes out of our naive assumptions on the structure of the theory.
How is it clear that B and C, we don't have any,
B is a charge of what we call fundamental string. C is a charge of another string, that is D, D1 brane, that is also a string. The change of a viewpoint R1 to R2 clearly changes fields B and C. Now, on the string side, I understand what string is, I understand what D1 brane is. Okay, I understood what Kaluza-Klein particles are. Now I want to understand on the string side what is okay, so you remember. What is D3 brane? So D3 brane on the string side. So D3 brane. So how it can come out from the supergravity side? How to get D3 brane? We know the structure of branes here in 11-dimensional super. We can still make a brane. We can take 5 brane. We can take 5 brane of 11-dimensional Sura. So I need to write it somewhere here. Brane of 11-dimensional Sura. And bracket over the torus. Complete. Okay? And you may see that it would correspond to D3 brane. So we may play the game of checking tensions. Tension of these three braids should be M11 6 times R1 times R2. Okay, so you see I already, let me call it 3. Now, from the point of view of superstring theory, I think that it is D3 braid. So how could it be if it is a D3 braid? I need to take M string to the power 4 and divide by G string. Okay? So let me check. It is R1 squared, and here I have M13, M11 to the power 6. I am using formula 2. Now, GS is R1 over R2. So that's how I'm getting R1, R2, M11, 6. Formula 3. You see it works? Now, let me make one more corollary out of it. You see, what we used to call D3 braid is invariant under S duality. Okay, I think I can. So it was a string theory side. So D3 braid was a D braid for what we used to call fundamental string. But at the same time, because of S duality, we say that it is also a D braid for D1 string. And if we study a theory on D3 braids, we can interchange fundamental strings and D1 strings by S duality. Now, we predict that there is some kind of four-dimensional field on a stack of D3 braids has particles of at least two types. So I would say that there are PQ particles, but it has particles of at least two types. With different masses. And there is kind of asymmetry that interchanges them. And now I would like to make an announcement that this is a M theory. M theory proof of Montagne olive duality.
Yeah, but strictly speaking, Montagne olive, as far as I'm concerned, is for billion gauge.
No, Montagne olive is proved for a billion gauge. Montagne olive conjecture. Okay. Conjecture. For n equals 4, d equals 4, super. And I will put proof in quotation marks. Because you cannot make a proof based on something that was not strictly defined. I assumed the U duality.
Yeah, but I thought that the von William gauge group, like the gauge group slightly changes when we perform S duality. While here you kind of say that the configuration of D3 is invariant under this duality. So that will imply that the gauge group should stay the same, which I think is not wise.
You see, concerning the gauge group, it is GLN, for this particular case you will say, it is GLN versus GLN over ZN. So this is the change of the gauge.
Yeah, but by your logic, D-branes, they are invariant under S duality. So the stack of D-branes seems to be also invariant under S duality.
Yes, but I have not explained. So I want to say that there is a
Yeah,
transformation.
but like supposedly the geometric configuration of D3 branes defines you a gauge group uniquely. And
Okay, but
so that's why there is this issue.
so I agree. There is an issue. There is an issue about here. There is an issue about the end.
Yeah, so that's why I kind of suggested to go a billion, where it is.
But for a billion, it is a theory, so it's not that interesting. For non-abelian, it is interesting. So how people work with all this business? They are studying different compactifications of supergravity. And then they're applying dualities. And then they say that something equals to something. And when something equals to something, it is of course a conjecture, because when I said that one thing equals to another thing, it was still a conjecture. So the very beginning of my today's, not evening, but the very first talk, is a conjecture of U-duality. And I gave you some evidences. But starting from this conjecture, you can derive many corollaries. And sometimes these corollaries would be reformulated as mathematical conjectures. And these mathematical conjectures would be proven. So this was called the game with duality. So people were playing like almost 30 years with this duality, finding more and more conjectures that turned out to be correct. Okay, so how much time do I have?
1 hour has passed.
1 hour has passed? So it means that we need to make a short break. And then I will talk for 30 more minutes. Okay? But before, I am ready to answer questions.
So you said about those apparently numerous conjectures that were motivated by these dualities and then proven. Can you give
At least.
no, not a list, like a concrete example, like some kind of statement, or is it some mathematical statement about some, just to see an example of something like concrete, because this is kind of fields and dimension matching and parameter matching. It would be interesting to see how some kind of concrete statement can be.
So we had a talk at the seminar about equivalence of the category of so there is Calabi-Yau, there are sheaves that are supported on 4 manifolds inside 6-dimensional Calabi-Yau, and also some skyscrapers and also some sheaves supported on 2-dimensional sites. And there was a conjecture that if you compute something about it, you'll get a modular form. So typical conjecture here is that you study the Euler characteristic of the modular space of instantons. And we call it f of q. And q is known to be 1 for the instanton at something like this. And then the statement is G naught squared going to 1 over G naught squared is the modular transformation. So probably here I have I or minus, I don't remember. Yes. Then this is a modular form. It's a type of conjecture. But people try to prove it. But you see, all these mathematical conjectures are kind of corollaries of the main conjecture. And mathematicians are happy to prove these mathematical conjectures because they cannot understand the main conjecture. So what physicists need the understanding of the main conjecture. While mathematicians are happy that they can prove something, so my conjectures were just that something equals to something, that some number equals to another number. And I went through it today.
Oh, I have a question. There is a D minus 1 brain in superstring set. And is the D minus 1 brain KK particle?
It's not a particle. D minus 1 corresponds to a pointer in the space-time.
Oh. Oh. So how about the tension of D minus 1 brain?
It's not a tension, it's a number.
Or is number?
Значит, я хочу поговорить про T-duality. Sorry. I'd like to speak about T-duality. Suppose I have an original system. Described by this action, quadratic. So it's quadratic Lagrangian, and x is identified to x plus 2 pi. And r is the radius of a circle. And there could be other x's. And I don't care about that. So this is the action of the fundamental string. So what I'll talk about is T-duality from the perspective of fundamental string. T-duality is a mysterious concept. Because as you see, everything is mixed here. Everything is mixed. We don't even know which string is fundamental string. But let us pick up one of the string and let us consider it as a fundamental one. And here I put m string square.
What is R?
R is the radius of a circle.
Then X should be identified with X plus 2 pi R.
No, x is identified with x2 plus 2 pi. And R here is the target space radius. So I have a circle. There are two ways to understand the circle of length R. One is to say that metric is 1 and x goes from 0 to 2 pi r. Or I can say that x is identified with x plus 2 pi and metric depends on r. So I'll choose an opposite way. I'll choose this one. Now, I want to say the following. I want to call dx f and sf is equivalent to ms squared r squared integral over sigma f VHF, and here I put a Lagrangian multiplier that makes f dx, and I call it y. So when I integrate over y, I see that f is dx, and I'm back with the original field. But now I will do another thing. I will integrate by parts here. I don't care about signs. And now, instead of integrating over y, I will integrate over f. It's quadratic integral that I am able to take. And I see that original theory and resultant theory are equivalent.
So there is kind of small issue because the original x lies on a circle.
Yes.
So the condition that df equals 0 doesn't quite imply that f equals dx. So you also need to impose the Arnold holonomy for f. So And taking into account this condition will eventually lead to the fact that field y, which is now real value, will also become a value. of
Yes,
threshold.
I admitted this.
Okay, but that's kind of leave it as an exercise. So-
Yes, I admitted this.
So kind of, there is a kind of more careful way to doing this procedure, which will result in y also being
Circle
by the
value.
audio field.
But here I see that I may understand what happened as ms squared 1 over ms to the fourth r squared, and I call this r dual rt RT dual. Now, why I am keeping this ms squared here as before? Because I have other axes.
Why do we say that these are dual? We then specify the dimensions so that x, like originally was,
One dimension.
yeah, but then y is something, well, if x was like a function or a one form, or like, and y could be something
So sigma,
k
sorry, sigma here was two dimensional.
form.
So it's point of view of the string.
Right. So y is also.
Yes, so f is one form. So y is also a function. So I will say that RT is 1 over ms squared r. So I am taking this ms square out because there are other x's. And these other x's contain this tension of the string ms squared. So I would like to keep it up. Now, I need to say something about deep brains from this perspective, not just writing the pictures. And here I will use something that you may or may not know from string theory. So if you don't know it from string theory, you may just keep it as it is. So in the string theory, we have a surface sigma, it has a boundary gamma, and we would like to impose some boundary conditions here. Boundary conditions. What kind of boundary conditions we should impose? One needs to know that on sigma we have a theory like dx star dx plus b bar c plus b bar dc bar. So these are called matter fields, these are called Gauss. And it has QBLST. That is C, energy momentum tensor for left movers. I will write it down. dx plus C bar. Energy momentum tensor for right movers. Plus BC bar. But I will not need here. And this guy is called GBRST curve. So what are good boundary conditions? Good boundary conditions on gamma are such that GBRT restricted to gamma is 0. In this way, QBRST is a symmetry of the string theory. Now, what do we know about the boundary? We know that on the boundary, C restricted to the boundary equals to C bar restricted to the boundary. Basically because C corresponds to diffeomorphisms, and diffeomorphisms should take boundary into boundary. Probably here the sign is minus, so let me take it minus for simplicity. I don't remember the sign. Now I want this restricted to the boundary to be equal to 0. Restricted to the boundary means that you are taking derivative only along the boundary. So there is the boundary condition. And the boundary condition is that x restricted to the boundary is x naught constant. These are called Dirichlet boundary conditions. However, there is another choice. Another choice is that you have cancellation between these two terms. And this cancellation could be achieved if you consider normal derivative on x to be equal to 0. And these are called normal boundary conditions. So the Dirichlet boundary condition could be also rewritten in the following form. Now, the statement that I'm trying to make is that if you go from field X to field Y, then the Dirichlet boundary condition go to Neumann boundary condition. Really, you may see that dx equals star dy. And star operation rotates tangent to normal. So if you had Dirichlet boundary condition on X, it would correspond to Neumann boundary condition on Y, and vice versa. So this is an explanation of the rule. Waste is going to rest. I can say more. Suppose I have this situation. So then I have fundamental strings that go this way. Start on deep brain and end on deep brain. So these are winding modes. And when I do P-duality, I replace the winding mode of the string to momentum mode. So here we have power, and here we have 1 over R T transform. So you may try to see it from different perspectives. Okay? And it's important to understand it. It's an explanation why, when we have superstring of type 2A over S1, we will go to very different theory after T-duality. That all D branes would change their dimensions. Wrapped would go to unwrapped, and unwrapped would go to wrapped. And they can write down like 10 formulas about it. All formulas would be as elementary as these are, as these formulas. Okay? Now, I want to keep this board to do exactly what Tim wanted. And I would like to say that this dx star dx was a theory on a string. And what could be a theory on the D brane? Okay? Question. and I'll immediately give an answer. It is maximally supersymmetric Young-Mills. It's better to call, say ND branes. Maximal supersymmetric Young-Mills field in corresponding dimension. Example. In D equals to 10, super Young-Mills is trace F YHF plus Fermi. And we are not interested in fermions at all. How to go to lower dimensions? You take some fields AI, I, equal B plus 1, etc. Then consider it just scalar field. And write down corresponding action. You will get still trace F region. And here we have your xd plus what? You will still have kinetic terms here. You see, now they are scalars. Plus, you will have interesting terms.
So you mean we treat them as just scalar fields?
Yes, so we are doing dimensional reduction. So we treat them as independent on coordinates. So we say AI depends only on x small 1, x small d. Okay, probably it's better to put here a trace. Overall trace. So it's still Young-Mills in lower dimension, plus kinetic term, plus potential. Probably here I need to put covariant derivative. And here I have potential. Now it's interesting to see that if potential is 0, when AI, AJ commute, then AI form 10 minus D commuting matrices. And since they are commuting matrices, I can diagonalize them. And I will say that AI phi 1 phi I1 phi IL. So how I'm going to understand these phi's? I'm going to understand these phi's phi I K R I coordinate of K braid. Just separated braid. So simplest example, is when I runs only one. So we have one coordinate. But we have, we have I equals 1. It means that we have only one space-time coordinate. And for this I equals to 1, we have n numbers. And these n numbers are n D braids. I know that it takes time to get used to this, but that's how it works. So it's called a stack of braids. So when I put them apart, I can consider only one blue thing. But I can also put them together. And when I put them together, I'm getting non-abelian theory. Interestingly enough. Let me comment on it. I'll write it in blue. On each braid, I have fluctuations of its position. You see, it would go like this. But also I have strings connecting them. And this is something messy. So we understand it as a W boson. So really, consider such an action and put some vacuum expectation value to fields AI, such that potential vanishes. and you will see so-called Coulomb-Higgs branch. It's that. So I'm proving it. I'm just explaining what do you have. And now, let me show some dualities using this assumption. Consider D2 brane in 10-dimensional stacked to any superstring. Single D2 brane. So it's a three-dimensional theory, right? It's a three-dimensional theory, so it has action dA star dA, and these are forms, plus, okay, let me call them small a, plus dAi star dAi. And here I goes from 1 to 7. And I understand it as something three-dimensional in 10-dimensional space. Could we imagine something three-dimensional in 10-dimensional space? Of course we can. These fields correspond to the change of embedding. So if you cannot imagine three-dimensional or 10-dimensional space, you can imagine one dimension in two-dimensional space. There is one-dimensional in two-dimensional space. And there is another, one-dimensional and two-dimensional space. So how do they differ? So they differ by this deformation. And this deformation is exactly AI. In this example, I had only one A.
You mean capital A?
Capital. So capital. So scalar field just shows you how you shift your embedding. Now, what's interesting? I can apply the same procedure that I unfortunately erased. Here, duality. Like T-duality. Remember that I have something three-dimensional. So A small was a one form. Dual to one form is a scalar. So if I apply here duality, I will get d5 plus daa star daa. So instead of 7 fields, I will get 8 fields. So it means that this theory is equivalent to something that has 8 and not just 7 perpendicular directions. Here the 11th dimension is showing up. Just that simple.
Can you say once again, what's the meaning of phi here?
Dual to A.
Uh-huh.
dA equals star B star. Moreover, when I'm writing this as a Young-Mills, I need to put a coupling. How do I put a coupling? We know how to put a coupling in front of Young-Mills. What would happen after duality transformation? This 1 over G naught square comes here. Wow, we know it. This is the radius of 11th dimension. So this is another test of the main conjecture.
So what happens to covariant derivative? Like your strictly speaking, like capital I should covariant derivative with respect to little I. Then you have covariant derivative.
Here, it is the case n equals 1.
Ah, okay.
It is the case n equals 1. You see, it is kind of elementary. I'm not using any high mathematics. You may do it yourself. You may check what I'm explaining to you by yourself. Yes?
Phi is scalar with period 1. Period.
Yes.
How it follows?
Because the gauge group here is compact.
So you need to also impose an additional condition that there are no flux.
Yes, of course.
So
Of course,
action.
of course.
That
So it means that when n equals to 1, I consider U1, not R, as a gauge group. So if the group is U1, it means that flux is quantized, and as a result, the dual
scalar field.
The dual scalar field lives on the circle. And it's exactly that circle. So it could be a starting point. Would people knew in advance what the branes are, they could develop theory from this place. And this is appearance of 11th dimension. You start with a string theory that is 10-dimensional. You study D to brane. Oh, you see brain in 11th dimension, and it is of course M2 brain. That lives in 11th dimension. In 11 dimensional theory. And I would like to conclude by today's talk. By considering case where we have D3 brane, single. So it's an abelian theory. You do duality transformation here, and you see that A goes to A dual. That is again A1 form. But 1 over G naught squared goes to G naught dual squared. It is the same transformation. One click that I'm applying in three places. In T-duality, in finding 11th dimension, and in explanation the simplest form of S-duality.
So here the integral is over sigma 4.
Over, yes, of course, over sigma 4. So we studied integral over sigma 2, over sigma 3, and over sigma 4, and we were successful in all cases. So you may play with other cases.
So this trick with kind of introducing majority field and integrating looks like a purely Bosonian trick.
Yes.
But is there some kind of argument why we should expect that the supersymmetry transformation will also kind of interact nicely with this string? So like how do people argue about sort of preserving supersymmetry under this T-duality?
So for a single brain, it's obvious. For a single brain, bosonic
No, it's
conformity.
far from obvious, because let us look at supersymmetry transformation. So normally you will have like field A transforming, shifting by a fermion, by corresponding kind of green, or sorry, not green, or photon. But then you want to kind of replace not field A, but dA by star df. So you will get a supersymmetry transformation for star df as.
Yes, I have not studied this issue.
So I was just kind of curious how people get around the issue, because at some point I literally tried to kind of straightforwardly implement it in 3 dimensions, and apparently I failed. So there probably should be some trick or similar auxiliary field and some transformation of fermions maybe. Or maybe some superfield formalism which allows you to treat like purely bosonic duality as a duality in supersymmetry.
So my answer is I never have done.
Oh.
Okay, actually today, in the morning and in the afternoon, I told you a lot. I told you even more than I was expected to tell. But all computations are elementary. Which is the point. There are several simple axioms. And you say the axiom is that action on a D brain is a reduction of super Young wheels. Basically, that's it. And then you can derive everything. So in the year 1995, there was a great boom in mathematical physics community, because a person who knew nothing about that was able to jump in and start writing papers. Okay? So I would prefer to have questions.
So there, where we have these kind of eigenvalues as coordinates, it all looks like some kind of matrix model.
Yes?
Is that the connection between matrix model and screen?
In some sense, yes. Because in matrix model, you have this potential. However, the question is what type of potential do we have? And here potential is commutator squared. Okay, let me correct myself. It's not commutator squared. In this form it's already like
Quick question.
yes.
Okay, can you use D4 brain to say something about the brain? So you start from 5D, pyramids, and
Okay, so now let us see. So let's try to do the same thing. Consider D4 brain. Once again, dA, star dA, and here we have sigma 5. Okay? And if I use duality, I think that in this case I will get two forms. So I see that for a single 5 brain, I get a theory of the two form for a 5 brain. And then, of course, the number of perpendicular is 5. So it's the only thing that I can write about it. So here I have the sigma 5, and here I have 5 perpendicular directions, yes? Then, the question that you may ask is the following. But it is not enough, because it should be M5 brain placed, not wrapped. So if it is placed, it should have some orthogonal deformation. So the question is, where are they? I have a conjecture at the moment, but as there are, I was not planning to talk about them right now. But there is D4 the zero bound state. And these before the zero bound states should correspond to the motion in the perpendicular direction. But today is too late to explain bound state.
So, now you're considering M5 brand up down the service up, right?
No, so here M5 brain is just placed. It's not wrapped, it's placed.
So to get the D4 brand, it's
To get a D4, sorry, maybe you are right. So to get a D4 brain, right, to get a D4 brain, I need to wrap.
yeah.
I need to wrap it. So it is M5 brain wrapped. So what I can say that it has this type of action. It's wrapped. It has only 5 perpendicular direction, but being wrapped, it should also have excitation corresponding to momentum that you have in direction that you are wrapped.
Yeah.
And this should be D4 D0 bound state. So that's what I think. And we will discuss these bound states next time. They are important. And what else do I have here? So it was D4, and then the last is D6. And for D6, it is very interesting because the action for D6 is DA star DA, and you have how many? You have three AIs. And here you have one form, and then you will get 3 or 4 form. I'm just trying to, probably 4 form you will get.
Yeah.
So it should be something like this. So this is supposed to be a theory on D6. And then it's interesting to compare it with so C should be 4 form, yes? So I don't know what this is. But idea is clear. That's how I'm going through different brains. Take super young Mills, and if I'd like to see it from another perspective, do duality. And actually you can do T-duality and S-duality and then again T-duality, and it will bring you the group of dualities. Let me say something about this group of dualities. Dualities that are called the S-duality as dualities. So they correspond to symmetries of the type AL, like permutation as dualities. T dualities correspond to Dn. And if you put them together, you will get E. You will get a Coxeter loop of the lattice of type E. So I have not checked it, but it's kind of an exercise. So in 90s, in second half of 90s of the last century, young people were training themselves in performing this duality. You know, in 50s of the last century, they were training by computing Feynman diagrams. In 70s of the last century, they were counting loops in QCD. In 90s of last century, there were, in the 80s of last century, they were studying conformal field theories as crazy. In 90s of the last century, they were studying this simple stuff called different duality. And then the year 1998, no new ideas were coming. And people were very sad, and there was a paper of Moldasena on ADS-CFT, and when people were drunk at string conference, they were dancing, shouting, "Hey Moldasena." So reflecting the popular song, "Hey Macarena." Of course you don't know this song, but you know who Moldasena is. So this is a brief story of, so it was an introduction to these dualities. I just want to say one thing. You can do it yourself. It is understandable. No mystery. No gamma function integrals. No rational values of zeta function. Or not single valued values of zeta function. No compactifications of complicated modular equations. This is elementary. This is not completed, but it is elementary and it works. I will put it this way. And this is actually the reason why I wanted to read this introductory course. Because you are coming to seminars when people are saying, "Oh, we put this brain, we put that brain, we do this duality, we do that duality," and you are lost. It's not good. You shouldn't be lost. My message is that this is understandable, this is doable, and this is also checkable. And the only way to understand it is to study some path of dualities by your own. Just trying to answer a question, what this is, what that is. Okay. That's all false. Tim, was I using something mathematically complicated?
Not on the surface.
What?
Not on the surface. There is no obvious stuff on the surface of the board, but behind it.
You see, since nobody knows what is behind it, it's like black hole. Here we have a horizon.